All right, 5.2 is properties of rational exponents and radicals. We're going to do half of it today, and then we'll finish the rest out tomorrow. Some of these properties you should already know. So as you look here in the core concept on the first one, they call it the product of powers. Okay, meaning I have like bases. So for example, I have x to the third times x to the fifth. Product meaning multiply, right? Okay. What do I do with my exponents here? I add them. Okay? 3 plus 5 is 8. That would be x to the 8th. Okay? Now, this does not change if the base is a number. Okay? So, for example, if your base is 6 to the 3rd times 6 to the 5th, your answer is 6 to the 8th. Okay, so you can do things with your numbers and exponents without taking 6 to the 3rd and then 6 to the 5th and then having two huge numbers and multiplying them together.
But they have to be both sixes?
But they have to both be sixes, yes. Okay, they both have to have the same base. Bases have to be the same to be able to combine things. Okay, so the next one is power of a power. Again, we just went over some of these. If I have x to the 3rd to the 5th, what do you do with those two exponents? I multiply them. Power raised to another power, so it would be x to the 15th. Same thing. If I have 7 to the 3rd to the 5th, that's equal to 7 to the 15th. Again, I don't have to take 7 to the 3rd and then raise it to the 5th power. I can multiply those exponents first and just have 7 to the 15th. Okay. Power of a product, meaning I'm taking a product, let's just call it x times y, to the 3rd. Does that cube go to one or both of those variables? Both of them. So I have x cubed, y cubed. Okay. So over here with a number, if I have 12 times 3 all to the 1/2 power, this would be the same as 12 to the 1/2 times 3 to the 1/2. 1/2 exponent is the same as what? Square root. Good. Okay. Negative exponent, we just recently talked about this. If I have x to the negative first, let's actually go with a number, negative 3rd. How do I get rid of that negative exponent? I move it to the bottom. So it would be 1 over x cubed. Same rules apply if it's a number. If it's 6 to the negative 5th, that's equal to 1 over 6 to the 5th. Sorry? Cross the line, change the sign, is the rule that I said. Cross the line, change the sign. Zero exponent. X to the 0. You guys know the rule for a zero exponent? Anything to the 0 power is always equal to 1. Not 0, that would be the multiplication. Okay? So even if I have a number and I take 9 to the 0 power is equal to 1. Might as well keep up my color pattern. Okay. The next one is the quotient of powers, meaning I have like x to the 5th over x squared. The other day when we did this, what did we do if we were dividing? You subtract your exponents. So x to the 5th over x squared would be equal to x cubed. Okay. What if I have 6 to the 3rd over 6 to the 8th?
That would be 6 to the negative 5th. So would you make that 1 over 6?
You would. So technically it would be 6 to the negative 5th, but we talked about a minute ago that's the same as 1 over 6 to the 5th, correct? Could you subtract those exponents if those were not both 6s? No. They have to be common bases. Okay, their bases have to be the same.
Like if one was a 7, one was a 6,
You just wouldn't do it. Yep. Or you could,
There'd be no solution.
no, I mean, with numbers there's always a solution, right? Okay, so in that case you would just take them to their power and just write your big old fraction. Or if it wanted a decimal, you could give it as a decimal. Okay, the last one, I forget what they call it, power of a quotient, meaning I have x over y to the 7th. Okay, just like with power of a product, that exponent needs to go to both of them. Okay, so it would be x to the 7th over y to the 7th. Okay. So if I have 5 over 7 squared, it would be 5 squared over 7 squared. And again, you could actually evaluate that out as 25 over 49. Okay, those are all the rules for your properties that you should have already learned at some point. Okay, we should know those or be able to recognize them. Okay, so taking a look real quick, we're not going to do a bunch of these ones, but we are going to do a couple here. Let's take a look at, some of these just tend to confuse people. Those actually all look like really good example problems, so we might do more than I planned on. 13 to the 1/3 times 13 to the 1/6. First thing you need to check is make sure you have like bases. Do I? Yes, the base is currently 13. So when I multiply, I'm going to do what with my exponents? I'm going to add them. What makes this a little bit more challenging than the other ones we've been doing? They're fractions. When I have fractions, what has to be true about them to be able to add them? They have to have a common denominator. So instead of 1/3, I need a base of 6, right? So my denominator is going to be 6. My numerator is going to have to change to 2. So 2/6 plus 1/6 is 3/6, which is 1/2. And you should be able to do some of that simplification in your head. I'm going to skip that one. I think you should be okay there and there. Let's do 8 divided by 8 to the 1/9. First of all, like bases. Yes, so we're good there. I'm dividing, so I need, need to be doing what? Subtraction. What is the exponent here? It's 1, right? Which, with a like common denominator, would be 9 over 9.
And then we change the 8 to a 7. Since you're the 9 over 9.
I'm not sure. Oh, no. This? No, because 9 over 9 is equal to 1, right?
But that would make it 9.
This is only your exponent. Okay, it's 8 to the first, right? 8 to the 1 over 1. Agreed? So a common denominator I need to multiply by 9. I would have 8 to the 9 over 9. It's not like we're adding mixed numbers. I get where you're coming from. It's not a mixed number. It's your exponent. 9 over 9 is still just 1 as an exponent. So then 8, those 8s, I subtract my exponent, 9 over 9 minus 1 over 9, 8 over 9. If I asked you to write that as a radical instead of a rational exponent, what would your radical be? It'd be the 9th root of 8 to the 8th power. Good. Okay, you're going to have to be able to transform it back and forth between those things, especially here in a little bit. Okay, and then the last example of these that I want to do, I have 56 to the 1/4 divided by 8 to the 1/4 all raised to the 3rd power. What do you think, Grant?
Would you take the 56 and the 8 and make them into radicals?
That's definitely one possibility, yes. And that would actually be personally my favorite way to do it. What do you think, Trayson?
Could you simplify it?
You can. What would your reasoning be on why that's allowed this time and not other times? Okay, so the reason that works, and both Grant and Trayson are right, okay, I like to do it how Grant's talking, okay, some people don't like that, which is just fine, okay. Grant's saying, could you change that to radicals? Yeah, you could say that's the 4th root of 56, and that's the 4th root of 8. Can we all agree on that? That has to be true, correct? Okay. Well, since I have common radicals, I am then allowed to, if I choose, I could write it like this if I wanted to, because it's the same radical for both of those. Okay. Now I can do what Trayson was saying and reduce. What is 56 divided by 8? 7. So I have the 4th root of 7. Okay. Now in this specific problem, that's probably going to make it a little bit more difficult changing it to a radical. Okay, it's just going to add a step is what it's going to do. Maybe 2 steps. So what they're showing, and if you look at your example in your book, I'm pretty sure they do it this other way. I'm pretty sure they say, since these have the same exponent, which like Grant said, is the same radical, but since they're the same exponent, I can just do this if I choose, because that's still saying the 1/4 goes to both of them, right? Okay, and then it would still be to the 3rd power. Okay, all I did is I took that 1/4, I said it goes with both of them, and then I would do what Trayson said. 56 over 8 is 7 to the 1/4 to the 3rd. Now we have, what's this called? Do you remember? Power of a power. What do we do on power of a power? We multiply on power of a power. So it's 7 to the 3/4. Okay. Now there will be problems where they want you to take it from a rational exponent into a radical form, in which case the first way we talked about, or what Grant said, would probably be the easiest way. Okay, so just make sure you're reading those directions. Do they want your answers in radical form, or do they want your answers as rational exponents? Okay, meaning fractions. Okay. That takes us kind of into the idea on our next core concept. Yep, this would be the 4th root of 7 cubed, if you needed to. Okay. That takes us kind of into our next core concept. They're talking about your product property and your quotient property. Okay, don't let them confuse you with this. what they're telling you is if I have, for example, I'm not going to do the letters like they have. Well, they show two completely different things on the example and the definition. Okay, but essentially what they're showing us is if I have two numbers under a radical, let's just use a cube root because it's a little different. If I have 7 times 4 under a radical, that's the same thing as the cube root of 7 times the cube root of 4. Okay, does that make sense?
Could you make that a 28?
Yeah, so that's where I was going to go with it next. So what you're going to probably end up seeing is they're going to give you this, and you're going to need to change it into this so you can split it up so you have a common base. So we can add it with something else. Okay, and we'll do some examples here in a minute. Okay, but what you'll be using this property for is so that, for example, let's say you want to add it to the cube root of, or the cube root of 4. Okay, so then you'd have 1 cube root of 4, and over here you'd have plus another cube root of 4. Okay, you're looking for common bases, trying to change it into that. Okay, quotient property, same exact thing. If I have the quotient of, they do 162 over 2. So like if I have the 4th root of 162 divided by the 4th root of 2, okay, they're saying that I can rewrite that if I choose as the 4th root of 162 over 2, which would be the same as 162 divided by 2 is 81. And then you could solve that. Anybody remember the 4th root of 81? 3. Okay, and that comes out a lot nicer because if you think about this, 4th root of 2, that's obviously going to be a decimal, right?
Yeah.
Okay, so you don't want to mess with that. But if you can rearrange things and write it using a quotient property, we can end up with a whole number there for an answer. Okay, we always want everything in simplest form. Okay, so let's take a look here at an example. If they give me the cube root of 4 using the product property, the cube root of 4 times the cube root of 128. Is it possible to multiply those two things together?
Yes.
Okay, pretty easily because they're both cube roots, right? So this would be the same as the cube root of 4 times 128. If you have a calculator, go ahead and do that. What is 4 times 128?
512.
So I have the cube root of 512. If you have a calculator, go ahead and do that one. 8. Okay. Could you have done it the cube root of 4 times the cube root of this? Yeah. But the cube root of 4 is going to be a decimal, right?
Yeah.
Okay, so if you end up rounding that, you will not get your whole number of 8. Okay, so if we can get those numbers combined underneath one radical, then we can come out with our whole number answer. Okay.
You still get 8.
If you type it directly in, yes. Okay, again, same type of thing. You have to understand these properties like I talked about yesterday, because when I start throwing variables at you, if you don't know these properties, you're not going to be able to type them into a calculator with variables, right? So that's what you're going to have to know, these product and quotient properties for when we get to variables. Okay? They're using numbers because those are a little bit easier to start with.
Is there a way to put fractions into exponents into the calculator?
Yeah, with parentheses.
Okay.
Okay, now, this next problem, this next example, they're wanting us to write things in simplest form. So I have the cubed root of 135. Okay, and actually, before we do this, let's do something a little bit different. Let's do a refresher problem real quick. I have the square root of 72, and I want you to reduce that.
No.
9 times 3 is definitely 27, but you're close, Carly. 9 times 8? Okay, why are you guys choosing 9? Okay, so you have to take a perfect square out of this, correct?
Yeah.
Okay, so when I take a perfect square out, I have the square root of 9 and the square root of 8.
So
Okay.
you have 3
Square root of 9 is 3. Since I actually square rooted it, the radical's gone and I'm done with that side, right? Okay, so now I move on. I move back over here to this 8. Is there a perfect square I can take out of 8? I can take a 4 out. 4 is a perfect square. Square root of 4 times the square root of 2. What is the square root of 4? 2. I square rooted it. Radical's gone. I'm done with it. I move back over here. Can I take a perfect square out of the square root of 2?
No.
I can do 1, but that doesn't help us at all, right? Okay, so I'm done with that. What do I do with these 3 things? I multiply. So my answer is 6 square roots of 2. Okay? I call that a refresher problem because the problem they're going to ask us to reduce next is the cubed root of 135. Okay, now this is where I talked about just the other day. You need to get to a point where you recognize some cube roots. Okay, cube roots you should recognize. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is. Those are probably going to be enough to get you to where you need to be. Okay? Those 4 are going to be the 4 main ones you're going to look at. So I need to find, since this is now a cubed root, I need to find a perfect cube that divides out of this. You need to check 8, 27, 64, 125. 125 obviously not going to work, right? Okay, so what one of those other 3 does?
27.
27 does. So I take out a cubed root of 27. What times 27 is 135? 5. So I have the cubed root of 27 times the cubed root of 5. Cubed root of 27 is 3. I'm done with that because I actually cube rooted. I got rid of my radical. Is there any cubed roots that I can take out of this? No. So I'm done with it. So my answer is 3 cube roots of 5. Same exact process. You're just taking out a little bit different number. Instead of taking out a perfect square, you're taking out a perfect cube. Okay. Moving on to example, or it's still example 3, but it is part B. Okay, this is a little bit different. I want to make sure I'm... Okay, so this is probably going to be significantly different than anything we've ever done. Okay. We start with the 5th root of 7 divided by the 5th root of 8. And some of these, like this one, are going to take some practice. Okay. I need to get that 5th root of 8 out of the denominator. Okay, we have done some in the past. It's been a while. If I had the square root of 7 divided by the square root of 3, does anybody remember how I do what's called rationalizing the denominator? No? Okay. I need to find a way to get rid of the radical in the denominator. I'm going to multiply by the square root of 3 on top and bottom, because when I take the square root of 3 times the square root of 3, I get the square root of 9. That's a perfect square, right? Square root of 7 times the square root of 3 is the square root of, oops, I was adding, I was going to put 10. Okay, so I have the square root of 21 over square root of 9 is 3. Okay, this works because 3 times 3 is 9, which is a perfect square underneath a radical. Okay, difference over here is I'm going to need a perfect fifth root. Okay, now don't make it harder than it needs to be, because 8 is already 2 cubed, right? Okay, so what I would look for, instead of writing this as an 8, I would write this as a 2 to the third power. How many 2's am I missing if I already have 3 of them? I'm missing 2 of them. So I need to multiply on top and bottom the fifth root of 2 squared. I need 2 of them because when I multiply these, 3 and 2 is going to make 5, right? Okay. So on the top, I need to multiply by the same thing. Why am I multiplying by the same thing on top and bottom? If I'm, what is this equal to in blue by itself? 1. So I'm not changing what it's equal to, I'm just changing how it looks, right? All I'm doing is multiplying it by 1. Just a different form of 1. Okay. Since these are both fifth roots, can I multiply 7 times 2 squared?
Yes.
Okay, what is 2 squared?
4.
So I have 7 times,
4.
which is,
28.
so I have the fifth root of 28. And this is going to just take some practice to get these down. I'm not writing 4 because of what I have in the denominator here. I'll show you. So now I have the fifth root of 2 to the fifth. What happens when I take the fifth root of something to the fifth power?
It cancels out.
It cancels out. Okay, Carly, that's why I like to not put 4. Your textbook does show 4, but I think it makes it hard to understand why they chose 4. Okay, so if I have exponents that can get to 5, I know they're going to cancel out. So I have the fifth root of 28 over 2.
Is that all?
And that would be as far as I can go, yes. Okay, so let's say that this would have been a ninth root. I would have had to get this to be 2 to the ninth. I started with 3. How many more would I need? I'd need 6 more. So I would have had to done 2 to the 6th power here, if that were the case. Yes, Grant?
Basically what we're doing is we're finding the whatever root of the denominator, and we're just adding it to equal to the nth root.
Essentially, yeah. Because I have to get, the only way I can get this radical gone is to cancel it out. And to get it to cancel out, my radical needs to match my exponent.
Okay.
Right? Because squared and square rooting are opposite functions. They cancel each other out. Cubing and cube rooting, opposite functions. They cancel each other out. Fifth root and taking it to the fifth power, opposite functions. They cancel out. Okay. I was going to go further than that, but I think that'll be plenty for today. What do you think?
Yeah.
Okay. So we're going to stop there after example 3. And that means you should be able to finish through problem number 27 for tonight.